Welcome to Cambridge IGCSE Physics, Lesson 3.1, Understanding Acceleration. Today we explore one of the fundamental concepts in motion, how velocity changes with time. This core content lesson will build your understanding of acceleration, its mathematical definition, and practical applications in the world around us. Let's examine our learning objectives for today. By the end of this lesson, you will be able to: first, define acceleration as change in velocity per unit time. This is the fundamental definition you must know. Second, recall and use the equation A equals delta V divided by delta T. This mathematical relationship is essential for calculations. Third, understand that acceleration involves changing speed or direction. Many students think acceleration only means speeding up, but it includes any change in velocity. These objectives target Assessment Objective 1, which is scientific knowledge, and Assessment Objective 2, which covers problem-solving skills. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, acceleration, which means the rate of change of velocity with time. This tells us how quickly velocity is changing. Second, velocity, which means speed in a specific direction. Velocity is a vector quantity, unlike speed, which is scalar. Third, delta, the Greek letter that means change in. When you see delta V, it means change in velocity. The units for acceleration are meters per second squared, written as ms2. Understanding these terms precisely is crucial for Cambridge IGCSE success. Let's explore our first core concept. The fundamental principle states that acceleration measures how velocity changes with time. This means acceleration tells us the rate at which an object speeds up, slows down, or changes direction. The definition is, acceleration is the rate of change of velocity with respect to time. Mathematically, we express this as it equals delta V divided by delta T, or alternatively, V minus U divided by T, where A represents acceleration measured in meters per second squared. Delta V represents change in velocity, measured in meters per second, and delta T represents time taken, measured in seconds. The diagram illustrates this as a velocity time graph where the gradient equals acceleration. Notice how the steeper the line, the greater the acceleration. This principle is fundamental because it connects motion to time in a quantifiable way. Now we examine the experimental method for measuring acceleration. This follows Cambridge IGCSE standards. The apparatus needed includes a trolley to provide the moving object, a ramp to create controlled motion, light gates to measure velocity at specific points, and a data logger to record timing data accurately. The method consists of these steps. First, set up the ramp at a suitable angle and position light gates at measured distances. Second, release the trolley from rest and allow it to accelerate down the ramp. Third, record the velocities at each light gate and the time interval between them. Safety is paramount. The hazards include the trolley moving at speed and potential collision. Therefore, you must secure the ramp firmly and position someone to catch the trolley safely. The diagram shows the experimental setup with the trolley on the ramp and two light gates connected to the data logger. Notice how the gates are positioned to measure velocity at different points along the motion. Let's work through our first example. The problem states, a car accelerates from 5 meters per second to 15 meters per second in 4 seconds. Calculate the acceleration. We are given initial velocity u equals 5 meters per second, final velocity v equals 15 meters per second, and time theta equals 4 seconds. We need to find the acceleration A. Step 1, write the equation. We use the acceleration formula, which is it equals v minus u divided by t, where each variable represents the quantities we defined. Step 2, substitute the values. We write it equals 15 meters per second minus 5 meters per second, all divided by 4 seconds. Step 3, calculate. 15 minus 5 equals 10 meters per second. Divided by 4 seconds gives 2.5 meters per second squared. Step 4, state the answer. The result is 2.5 meters per second squared to two significant figures, with units of meters per second squared. Example 2 applies the same principle to deceleration. The problem is, A cyclist brakes from 12 meters per second to rest in 3 seconds. Find the acceleration. The data shows initial velocity u equals 12 meters per second. Final velocity v equals 0 meters per second since the cyclist comes to rest, and time t equals 3 seconds. Now we analyse. First, apply the equation. We use a equals v minus u divided by t, the same formula as before. Second, substitute the values. We write a equals 0 minus 12, all divided by 3. Third, calculate. 0 minus 12 equals negative 12. Divided by 3 gives negative 4 meters per second squared. Fourth, interpret the result. The negative sign means this is deceleration. The cyclist is slowing down. The graph shows this as a straight line with negative gradients, starting at 12 meters per second and ending at 0. The gradient equals negative 4 meters per second squared, confirming our calculation. Mathematical skills are crucial in physics calculations. Let's examine 3 key skills for acceleration problems. First, equation rearrangement. When we need to find a different variable, we rearrange algebraically, starting with a equals delta v divided by delta t, where a is acceleration, delta v is change in velocity, and delta t is time. To find change in velocity, we multiply both sides by delta t to get delta v equals a times delta t. To find time, we divide both sides by a to get delta t equals delta v divided by a. Second, unit conversion. To convert from kilometers per hour to meters per second, we multiply by 1000 divided by 3600, which simplifies to 5/18. This is essential for consistent SI units. Third, sign convention. Positive acceleration means speeding up in the chosen positive direction, while negative acceleration means either slowing down or accelerating in the opposite direction. Understanding signs prevents calculation errors. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a ball is dropped from rest and reaches 20 meters per second after 2 seconds. Find the acceleration. This tests your understanding of the basic acceleration formula with simple substitution. Question 2 is intermediate. It states, a train decelerates from 30 meters per second to 10 meters per second in 5 seconds. Calculate the acceleration. This requires you to apply the concepts we've learned to deceleration, remembering that the results will be negative. Question 3 is advanced. The question is, an object accelerates at 3 meters per second squared for 4 seconds. If the initial velocity is 2 meters per second, find the final velocity. This tests your analytical skills by requiring equation rearrangement. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how acceleration concepts apply in practice. In automotive technology, car safety systems use acceleration sensors called accelerometers to detect sudden deceleration during crashes, triggering airbag deployment within milliseconds to protect passengers. In sports science, athletes and coaches analyze acceleration data to improve performance in sprinting, where the ability to accelerate quickly from the starting blocks determines race outcomes. In engineering, elevator design requires precise acceleration control. Elevators must accelerate smoothly to avoid passenger discomfort while maintaining efficiency. These applications show why physics matters. Career-wise, physics knowledge leads to many professions. Automotive engineering designs safer vehicles. Sports science optimizes athletic performance. Aerospace engineering develops spacecraft and aircraft. And transportation design creates efficient public transit systems. The concepts you learn today become tomorrow's technological breakthroughs. Let's review the solutions. For question 1, the answer is a equals v minus u divided by t, which gives 20 minus 0 divided by 2 equals 10 meters per second squared. This is correct because the ball starts from rest and gains velocity uniformly. For question 2, we find it equals 10 minus 30 divided by 5, which gives negative 20 divided by 5 equals negative 4 meters per second squared. The negative sign indicates deceleration, as expected when braking. For question 3, we rearrange the equation to v equals u plus at, giving 2 plus 3 times 4 equals 14 meters per second. Notice the approach used systematic substitution. Now, exam success tips. First, always show you're working. Even if the final answer is wrong, you earn marks for correct method and formula usage. Second, include units in every step of calculation. This is essential for full marks in Cambridge IGCSE. Third, check if your answer is reasonable. Typical car acceleration ranges from 1 to 5 meters per second squared, so an answer of 50 would indicate an error. Fourth, read questions carefully. Identify whether the object speeds up, giving positive acceleration, or slows down, giving negative acceleration. Let's summarize today's lesson. The key points to remember are, first, the definition. Acceleration is the rate of change of velocity with time. This fundamental concept describes how quickly velocity changes, whether increasing, decreasing, or changing direction. Second, the equation AI equals delta V divided by delta T, with units of meters per second squared. This mathematical relationship allows precise calculation of acceleration from velocity and time measurements. Third, the sign convention. Positive acceleration means speeding up in the chosen direction, while negative acceleration means slowing down or accelerating opposite to the chosen direction. These three concepts form the foundation for understanding motion analysis. For further study, review velocity-time graphs and understand that gradients represent acceleration. Practice equation rearrangement problems to build confidence with different problem types. The next lesson covers forces and Newton's laws, which builds on today's work by explaining what causes acceleration. Ensure you understand today's concepts before moving forward. Remember, physics builds systematically. Each lesson connects to the next through fundamental principles.